about nuclear structure, imaging, hydrodynamics.
Thanks a lot for organizers for inviting me here. Very nice to be back here and add one new mug to my collection. Third one. So yeah, I'll be talking about actually a lot about similar things like nuclear structure, of course, so isobars and neutral skin and light ions. And yeah, it's really based on this work with Hovert. He talked already 2 weeks ago here on triactum, and also new work with Giuliano. So I have to kind of admit a little bit that I put this 3 parts, and funnily enough, yesterday on the schedule there was no break scheduled at 15:20, so I thought that I would easily have 1 hour. I have to admit that okay, but next week I also have a talk, so I think that realistically the third part I will not present. It will be mostly about this isobars and new results on the neutron skin. Yeah, so heavy ion collisions, hydrodynamics, nuclear structure. I think well, we kind of got quite convinced now, all of us, that this nuclear, the shape of nuclei and also nucleons. So Hobart talked about that. Is really important, especially if you want to get the details right. Like for these isobars, just a few percent effect, but we actually are really getting a little bit into this percent level science, and I think that's really exciting. And that's also why I really study this nuclear structure quite a bit. Even though it's relatively small effect, it's for us important and interesting to develop the field. Well, I mean, I don't have much time to introduce, but okay, I put this pretty stern picture here where we study kind of this heavy ion collisions. And it's yeah, I guess it's an advertisement for Royal Dutch Airlines. But as a small introduction, quark gluon plasma is interesting. It's strongly coupled. So it's just one of the main reasons why we study it. And also to introduce a bit for nuclear people is that how we study this. So you really have kind of these pancakes colliding. There could be jets produced, but that's really not an effect we're talking about in this workshop, I think. But then all these the quark gluon plasma and all these particles just interact a little bit and they expand. And that it's strongly coupled is important. So it's not just a few scatterings and particles come out at random. And the funny thing is that you can see this already if you just, well, there are billions of events, but if you just look at these 4 events from CMS in this case, you can see it by eye. So if it would be just random scatterings, because there are a large number of particles, you would get exactly spherical distribution, a bit like this one, which is a central collision. And here you see that it's really elliptical, or even quadruple, or it's also elliptical. And the explanation is really that, well, you heard it probably now quite so many times, is that you have this peripheral collision which has an elliptical shape, and the particles don't scatter randomly. No, it's really in hydrodynamic plasma, which has a much larger gradient in the short direction and in the long direction. And that's why there's a more push in this direction, and most of the particles will then end up in this direction. And that's what you see in the single event here. That's kind of the lessons we take all the time. And you really kind of see this V2 is just like the Fourier harmonics of this kind of distribution, and you kind of plot it as a function of centrality, where kind of these very central collisions are head-on, so they're more like spherical, and peripheral ones, they have this much larger V2, and this is actually a fit recently. I'll skip that part in view of time. Well, what we did ourselves with Hovert, which is really based on like a long part of research and of these different stations, and actually this model is kind of based on the Duke University a few years ago. So we have this triactum code. It's a public heavy ion code. You can all download it. It's originally done as Hovert's PhD project. That's also where the name comes from. It's the old name of Utrecht, the Roman name. Well, Hovert's very proud. It's very fast. I think he now kind of claims he runs 1 event per second, but okay, you have to kind of push the numbers a little bit in that case. But it's well, what helps us a lot, and that's also that's precision science for these isobars. You really need like millions of collisions, so it's important. And we kind of try to do all the cuts equal to experiment and to really make things scalable, including like parallel analysis. So that really works, and we really benefited from that in this analysis. I'll show you. It has this kind of initial stage, which has been kind of talked about for a few times, like this Monte Carlo Glauber with the nucleon positions, and you get kind of different shapes. And I'll say a little bit more about it. It has some kind of non-thermal stage with some non-thermal flow. It fluctuates, which is important. And then there is this hydrodynamic stage after like 0.5 Fermi over C, which is a parameter. All these kind of red numbers are the number of parameters that go in. So that also kind of indicates a bit that we're not super certain about what's happening here. So shear viscosity is a function of temperature, bulk viscosity is a function of temperature. There's like second order hydro parameters that are also significant. And then there's this cascade of hadrons, for which we use the SMASH code. And this is the kind of triactum framework. And okay, So it's really easy to use. This is this parameter file. It's a bit of an advertisement to go to Harvard's website in this case to kind of download it. And of course, it has this kind of, well, it is actually a real event. You really see also real time these particles coming out and smash, they interact still a little bit, they decay. And I left also the initial condition there to kind of show you again this kind of elliptical shape there. And you actually see all the particles coming out on this side and that side and fewer on the other side. So this is kind of how trajectum works, and then what you analyze and get all the observables out from. Now to get to the topic of the workshop, so it's the shape of nuclei. This picture I think Giuliano made. We had this big white paper. Many of the authors are here in the audience, so you kind of have these kind of collisions of different nuclei, of different shapes, and you get different anisotropies, and that's what we're interested in. And the motivation, of course, has been also shown many times. It's this kind of magnetic field of the isobars, where ruthenium and zirconium have the same number of nucleons with a different charge. So ruthenium really kind of trivially has 10% larger magnetic field. I think it's hard to argue against that. And then of course there's this famous plot where above you would discover the CME, and then below you would not discover the CME. And I put here like, unfortunately, no CME detected. And well, the unfortunate is really a question mark here, because it would have been a catastrophical disaster if it would have been above, right? Maybe you didn't know that it was like below because nuclear structure, which is kind of in hindsight obvious. But okay, it could have been a real train wreck if you would claim the CME is discovered because nuclear structure. But so 50-50, we were lucky.
Can I also make a comment? There are also that are insensitive to CME on the same point, so they will also be above one.
Yeah, it will still be discovered, but not as big of a disaster as could have been. No worries. Yeah, good. So this is a nuclear structure effect. It's just the shapes are different, and that's why the P2 is smaller, and just also motivated by the CME, but not necessarily for the CME, because triactum, of course, in the beginning we didn't study this because triactum doesn't have magnetic field, so we cannot really study, at least at this moment, the CME. But we can study the nuclear structure, and that's also why we got interested after this plot, and we started only doing this at that time. So these Monte Carlo Glauber values that was also presented a few times. It's case 3 and case 2 very nicely this morning. So this was all done by Starr, and then there was this density functional theory also by Yang here in the audience, yeah, that also kind of got some new beta 2, beta 3 values. So what we decided is not yet this Bayesian analysis. Partly what's used to say it's very computationally expensive. So we just these 5 cases of different ruthenium and zirconium parameters. I could go into more details, but probably don't have time for that. So they're just like proton radius and skin thickness of the neutron. They could be different. This neutron skin is important, beta 2, beta 3. And here, that's the addition for this morning, is that, for instance, case 3, you can really see because of the cross section, which we computed. So you see that 4.86, 4.73. So this zirconium here is really bigger than the ruthenium. I think the cross section is the easiest way to kind of visualize it, which in case 1 is actually not the case. So, for instance, this Starr case 1 is very old electron scattering parametrization, pretty incorrect. So it even gets the size wrong. So these are 5 cases. For all of them, we simulate like 1 million events. And then in the hydrodynamics, so this is not like this kind of what we just had with the epsilon 2 that you match to the P2, which doesn't quite work. I'll show you. You really do the full computation, and it's nice that they have this fast code to do that. Okay, this is also a thing I figured if I would skip it or not, but there was quite some interest here. This is the same multiplicity plot we saw quite a few times before, ruthenium and zirconium, and this ratio. And there was this question before, why is this not monotonic? And first you just think, okay, probably the uncertainties are not right, so it should have been monotonic, but it's actually not the case. So it's also a bit of a motivation why you have to study papers carefully, why you have to do everything precise. The reason why this thing is not monotonic is because Starr made the choice that the centrality definitions, they are integer number of particles. And if you do that, there's a table in the paper that these integer number of particles, they don't translate to integer percentage of centrality classes. So if you look here at 20 to 30% centrality class, then this is just a label. It's not 20 to 30, no, it's 20.08 to 29.95. And in the other case, 19.96, 30.08. If they would have been the same non-integer values, it would not have been a problem, it would have cancelled. But since they are different, you really need to be very careful, especially for these peripheral cases where you're really dividing 15 by 14 and you get like 7% effect. So this is kind of how this curve comes about. So it's kind of important to get all these details up to like 0.08 right. We actually reproduce this here, this divides the centrality classes, even for V22, it still has like a 0.02 per mole effect. Here it looks like it's within the errors, but actually they're correlated. So that's why we did 2 cases, and this is really the effect that it has on V2, just because the centrality cuts are not at integer values.
Well, the ratios are not taken between the same centrality.
No, because in star analysis software, you cannot do non-integer centrality classes. So yeah, they have to update their analysis software. It's not, and they.
I don't think it's the analysis number of tracks you cannot cut the track in.
Well, you can, if you have like a number, if you have like 25 tracks, you can put half of them in one class and half of them, or 1/3 in one class and 2/3 in the other class. Of course, that's a bit arbitrary, but since it's the same thing, it doesn't matter that you get at least the right answer.
I mean, in principle, we can smear one track as a 0.5 to 1.5 uniformly. Then that will allow you to cut this arbitrarily.
Yeah, you can also make the measurement in integer tracks and then do a weighted average. There are many ways to solve this. It doesn't matter. We just copy these values into Reactum and it also works. So it's not really a problem. Well, it's just visually not very pleasing. That's the only problem. I don't have time to this, but they get to go through all these details. This multiplicity distribution, and this is actually a bit important because these are all the centralities, which I put the numbers up there, and at very low multiplicity, star doesn't know if there's a collision or not. It's an experimental uncertainty, and actually that's up to 50% the case. So to get this ratio right and interact them in the end, we get it exactly right, including all the hydro. What's the subtlety there is that these normalizations, they can be very different, especially because you don't know how many events are there from 0 to 50%. So this is kind of also, this question came back a few times, like, isn't it just that the centrality is ill-defined or not well-defined? So in this plot, this is just a multiplicity distribution. So how many tracks do you find in the probability distribution? So this defines then centrality classes. And I think in the end that was all done properly because from 50% onwards, so that's actually this orange line, that's all measured, and you fit a model through it, and that predicts how many events are here. And interacting, we did exactly the same thing, and it actually fits very well. And it's just like because you know that this from 50% onwards has to match, we could even divide in exactly the same way into Reactum the normalization and got this normalization also fine because there's a bit of an arbitrary number there because of this number of events there, but it all worked out. But you have to do it carefully, and if you want to do it carefully, you have to carefully go through all the steps of this slide. So then you get the centrality classes, and then you take the V2 and the V3 and the MPT in this case, and sorry, it's ruthenium, zirconium, and the ratio. And in this case, so now of course it got very interesting because we have 5 different cases we simulated, and we see that this purple one, especially for the V2, which was also, that was case number 5, so that's really well, yeah, I guess Yang Yong put this beta 3 value of 0.202. It's really the best motivated case, and with ruthenium being a little bit ellipsoidal, zirconium being a bit pear-shaped, and also with a neutron skin. So this was the best motivated situation. And well, probably also a bit accidental, but it went exactly for the data, so we were very excited. For V3, not exactly, so we're really a bit overshooting a little bit. So this indicates that probably the beta 3 was a bit too large, so it would probably be a bit smaller, and then this, especially at the ultracentral region, would be a bit lower. Now I think there is already MPT data out in this plot, in this paper, it was not on there. To make that even more precise, what you can already see at this plot is that for the central regions, you have a much bigger effect for V2 and V3. And this, of course, you can go to even more centrality, so ultra-central events. Here it's shown as a function of multiplicity, so then you can see that this is really like 0.01% is the last line here. And okay, so then also what Reactum can do quite nicely is that you kind of do like 250 million Trento events, and then it's a weighted analysis. So it simulates of the coin, the very, very central ones of these, it simulates more of them and fewer of the others, and it weights it appropriately. So you don't cut on like things like that and say that we define centrality like this, but we can oversample that, and we're still keeping the multiplicity distribution correctly, and that's why we can actually compute things to very extremely ultracentral values. And in the previous plot, you had only like 2% effect for the V2, and here you see like an 8% effect in the V2, and then more than 10% effect in the V3. And the reason is really, if you go to ultra central, well, there's only one way to really get such a high multiplicity, is that they're exactly aligned. So then you get exactly this nuclear structure shape. Right, that's the picture, of course, still fluctuations, but there's really good motivation for this, and computation is a little bit expensive, but it works very well. One thing that, of course, then what was said many times, but it's nice to kind of check it explicitly, is indeed like so. For instance, for in ruthenium and zirconium, both of them, we don't fit exactly the V22. The reason is also that reactant is not fit on these low energies; it only fit at LHC energies, but the ratio works very well. So what we then checked is, for instance, if you double eta over S, double zeta over S, half eta over S, how do the things change? And of course, the V2, the V3, and the mean PT, they change quite a lot. But in the ratio, not much changes. So it's an explicit check, which was also done before, I have to say, by other groups. What is important, and that comes a bit back to this previous talk about the Bayesian analysis, is that there is this kind of lore in the community, which is true to a large extent, that Vn is proportional to epsilon n. So we computed using Monte Carlo Glauber. But there is a coefficient here, and this coefficient, well, definitely depends on centrality. That's very well known. But what we found is that, yeah, that this coefficient also depends on if it's ruthenium or zirconium. And I think it makes also a lot of sense. It just depends on the size. And we're talking about small effects. Like if you're taking a ratio, the epsilon 2 changes by a little bit, the V2 changes by a little bit. So if the kappa changes by a little bit, whereas epsilon 2 and the leading order term is large, then you have a small effect times a large effect plus a large effect times a small effect. So you have to kind of do the product rule, and both effects you have to take into account if you want to use epsilon 2 as a predictor for this V2. So the lesson of this plot is that you should not take epsilon 2 as a real predictor for V2 if you want to take the ratio. If you want to be percent level accurate, which you need to be because this is kind of a percent level plot, then you need to take this kappa into account. And we prove this by this. Okay, it's a bit maybe messy, but this is V3, this is V2. So we just forget about V3. V2 is important. This is zirconium over zirconium. So it's the same ion, but we just changed the beta 3. So we just change the geometry. You see that V2 changes, and the epsilon 2 also changes. And there the ratio, this kappa is the same because it's the same nucleus, both zirconium. Here we get zirconium over ruthenium, and you see the epsilon 2 and the V2 change in a very different way. Except perhaps for this ultracentral beam. So there maybe you can use it, because here this is geometry driven. So this is really dominant by the epsilon 2, whereas here this kappa is very important. So it's kind of it's an important lesson if you want to kind of go on with these isobars using this epsilon 2, that you really have to do this properly. How am I doing with time?
You have 12 minutes and 20 seconds.
That's including questions or not?
No, that is not good.
Yeah, some questions. Anyway, so the new results on the neutral skin. So this is really for lab 208. But it's very good because everything was already more or less introduced before. So I hope that helps. I want to do a small introduction on Bayesian analysis, but usually I think did an excellent job. We just have kind of this prior is times the chi squared times the posterior. Well, I guess I made my point already that the sigma is really a correlated matrix, which is very important. It's very similar to what they do in gravitational waves. Many of these parameters are correlated, and that is then properly taken into account by a Monte Carlo chain. We have like 650 data points now, and then you obtain this posterior probability, and you check a little bit what you did. So how this looks in practice. This is kind of the design. It's like this 1000 curves for all the spectra and the V2. But then once you train the model, you can actually fit most of them almost. Well, not spot on. There are definitely a few problems, but most of it really goes through. I have one more picture, which is nice to show. Is this kind of after this is actually after taking the MCMC. So then we select often this is now the new thing we do standard. So after doing the whole analysis, we select 10 probable parameter settings. So these are from the chain. So all 10 of them are equally likely. And you see, for instance, I have a very different like build viscosity or shear viscosity, but all of them are allowed. And also the width are different. And here are like the initial energy densities. And yeah, actually, if you look at it, it's somewhat, how do you say, they look so different that you really wonder, like, really, can we not tell these two apart? And at the moment, we don't. What's also interesting of this plot, which is not so clear and goes into a lot of detail, is that most of the time, this dashed line and the solid line are more or less in agreement, but not always. Like here, there's a dashed line that goes through the data. This is V2, same plot I showed before. The solid line is the actual reactant computation. The dashed line is the emulator, like what Sushi was also talking about. So this is what we use in this MCMC. So here you see that this emulator is quite a bit off.
What are the, on the top of the 2D contour, what is different column? You're changing the W and changing the A and changing.
Yeah. So different column is different setting of the Bayesian
But they're
parameters.
independent events because the loops change a lot.
This is as function of centrality. So this is 0%, 10%, 25%.
Or from the most likely region in the posterior parameter.
Okay, but if you look at 25% centrality, then you look across to the right, they change dramatically. Are they-
Yeah. So
Different events? Or
different settings. So they even have different W. But the settings are all allowed by our analysis, at least so far.
so, but the global, the impact parameter fixed. So the-
No. These are then just
25%.
random. These are random events within the centrality classes. But indeed, I mean, you're right? I mean, if you look at this column, you see it's different from this one by eye. I mean, they're random events, but you see they're different because of the different W. And it's a little bit striking that this is the current analysis, we cannot distinguish this from the data.
What I mean is they're different global events. Even in the global level, they're different, right?
Yeah, this is random events. They're all random events constrained with these parameters, constrained with the centrality class. But yeah, like because for instance, what Giuliano was saying, okay, we can really see the shape, we can see this, and it's of course all true what he's saying. But given the data, we cannot really distinguish which one is true. So that's why I kind of like to produce this plot. The other thing I wanted to show with this plot is a bit of disappointment effect. Like I wanted to kind of show that there's correlations. Like for instance, if you have a large width like this one, with or very tiny structures, that you would get a larger bulk viscosity here than here. It's not very easy to see, and it's probably true because it's dominant here. So this one's a bit larger than this one, but here also large bulk viscosity, and it's very smooth. So it's a bit disappointing, to be honest. You don't see it by eye.
Did you include the total cross section in this analysis?
Yes.
And I thought that gave you better constraints on the W.
Yeah, it's true because the W is from 0.55 to like what you see actually is not so big, from 0.4 to 0.6, and it used to be 1. So if you do this with Jetscape, it looks completely
It was
different.
worse, much worse.
With Jetscape, you wouldn't even see any nucleons. Yeah, that's right. That's fairly recent. So that's the intro on Bayesian analysis, then a little bit of the conclusion on the neutron skin. So this Wood-Saxon profile has come about already a few times. So this is 1 over e to the power r minus r over a with like the,
Just one quick question on the previous plot. Did the heat map scale with the same color? Like is the, I guess, temperature or whatever you're showing there the same? Or is that varied from that much?
I think for presentation purposes, the red one is the highest point,
Okay,
because
that's not
otherwise
restricted that they-
it must be more denser here. Yeah, this is fitted to I must,
Arbitrary.
but yeah, it's not arbitrary, but it's visually pleasing.
Got it. All right, continue.
Oh, no. Good. So this Wood-Saxon parameter, and this is the value we use for all our simulations. So our for the proton radius 0.68, 0.69. So the radii are the same for the protons and the neutrons, but the neutrons have this diffusiveness. So this 0.56 really says, I mean, you see in the red line that it's much more diffuse and that there are more neutrons far away, and that's also why it's called the neutron skin. It's very important to stress here that these are values that we got from this review, which is displayed down here. Well, you can see it over there, Konstantin Lozoidis and David Anteriorios, Jason Kamin, where they did careful analysis, and this is really the point density of the nucleons. So it's not like the average shape of the energy densities, no, it's the average shape where the centers of the nucleons are. So, I mean, for this cross-section things or all these discussions we had before, I think this is what you should also use for these high energy collisions. If you boost something in the longitudinal direction, well, the transverse coordinates don't change. It's basic relativity. So the center should be at the same place, and this is really the correct shape. That's for this cross-section, and the cross-section is actually very important also for this neutral skin. So we wanted to see what we can say with heavy ion collisions about the neutral skin. And the obvious thing to do is, since we had all these Bayesian things, with all the parameters and all the observables, is just to upgrade this neutron skin, this 0.56 to a parameter. So that's what we did. So there's now a parameter there, we varied it, and we see what we can say. Well, this I don't have to repeat, like this is relevant for neutron stars, all of this you know. Well, can we make progress using heavy ion collisions? It's a bit relevant, like all of the computations are isospin symmetric, right? I mean, we don't have a neutron or a proton distinction in a way like, okay, they generate the same number of gluons, the same number of quark gluon plasma. It's just the shape that changes. Like the neutrons, they do have a different distribution than the protons, also in reactant. So, and then of course, the crucial part is that the proton distribution, you know very well, because proton is charged. So you just shoot an electron, you know it very well. So if you measure the total matter density, then you just subtract the two, and the difference we're sensitive to. So then we can actually get the neutron RMS radius. This I said, this Trento model, okay, I introduced a little bit, but not much detail. So I'll say a little bit more next slide. Yeah, good. And it's important, of course, that we don't only vary this one parameter and see how things change, because then, of course, if you want to, you really need this global analysis to kind of the width changes, the bulk viscosity changes. So that I think is important. These are then the first results, and it's actually a more accurate Bayesian analysis because we had to run it again anyway. So this is a 3000 design points. And this is as a function of AN, a few of the observables that show the biggest difference in this case. And the most obvious one is the cross section, the total cross section. So you see here that it really depends very sensitively on this AN. So if you kind of change the nucleon thickness to 0.75, you really get like almost 9 bars, whereas the data point is shown here. So that would be ruled out only from the cross section, I think. The multiplicity, here different centrality classes normalized to the experimental value. Quite a strong dependence in peripheral collisions, which also makes sense because if you kind of change the edge, you get more peripheral collisions, and you kind of get the multiplicity goes down there. MIPT, similar effect as the multiplicity. V2 doesn't change so much, and also doesn't change depending on the centrality. Good. So okay, one thing I didn't say yet, but this neutron skin of the Wood section is like this A parameter, and to compare with things like cracks, we convert this A parameter to delta R. So R is R neutron minus R proton, so this is really the neutron skin, and this Rn and Rp are the root mean square radii.
Can I ask you a question?
Yes.
So you are only changing the diffuseness and you're terming that as the neutron spin, but that's sort of an assumption that it only comes from the diffuseness. In reality, it comes from both the radius and the diffuseness. That's if that's a total slope. So I think there's a very strong assumption here.
You think it's strong? Yeah, we wondered a bit about it.
Really strong assumption here that it is, you are assuming it is only that one parameter. So that sort of leads to the first graph that we put as a small figure where you have only one axis as your variable, which is the diffuseness. And I wanted to understand what is the total cross section as in the first figure.
Where's that data come from?
Yeah.
Alice,
what
Alice. The hadronic interaction rate of lead-lead collisions at the LHC at 5 dB.
Can you just sort of define what that like? How do they get that percent?
Theoretically or experimentally?
Experiment.
No, you just you count the number of events and you measure the luminosity. The luminosity they measure by a Van der Meer scan, so they kind of put the beams.
Sorry.
Well, the beams first they're apart, then they kind of know the profile of the beam. They put them more into each other, so they kind of get a relatively accurate estimate how much lead is actually going in the beam. So then you know the luminosity. Then you count the number of events, and then you know the cross section.
So they are able to measure all possible reactions. That is what they are doing.
Well, there have like, of course, a systematic uncertainty. So 0 to 90% they can measure, and there's 90 to 10%, 100%. So 10% of them they have to estimate because of the noise and things like that.
So there's a 10% uncertainty.
No, because they can estimate that quite well. So the total uncertainty is 2.4%.
So let's leave any more discussion to the, because we only have.
Yeah, and also about this R versus A, because I think it's an important question. And to be honest, I mean, we thought more about it after we ran it. So for us, it's not very easy to fix this. But what we do think is, of course, you're right. Like if you change R, then this change the curve will also change. But what we think is that for the final result, we're mostly sensitive to the combination R and A that is sensitive to this delta R, the neutron skin. So okay, we find larger A, larger delta R. If we would vary all the R, then we probably would have a smaller A. So they would be very highly anti-correlated and would be mostly sensitive to the neutron skin.
So Bill,
it's a bit of an assumption.
At this point.
Let's talk about it because it's an important question. Oh, how much?
Less than a minute.
Yeah, but this is the final result. Okay. Well, okay. So less than a minute. So you get all these parameters, you get all the posterior and the correlation, all that. So I focus here on a few which are very relevant. So this is the neutral skin. So this is really the distribution. That's the result. And what is very nice is that it's actually the strongest anti-correlation we find in our posterior at the moment is that this P parameter in Trento, as experts will know about it, the Trento is this formula and it's skewed over P, is very strongly anti-correlated. So P also determines a bit of the shape of the multiplicity distribution for centrality, and this neutral skin does it as well. So it's very nicely explained, it's very consistent. It also depends on the cross-section, but given the cross-section and these multiplicity distributions, given the Bayesian framework, both of them are very tightly constrained and they're very anti-correlated. That's the message. So,
Do these axes have a scale?
yeah, the axes scales are then displayed here. I should still program this because in this case it doesn't fit, in this case it does, and okay, then I put them here. So it's 0.45 to 0.75, and yeah, these are the other scales. Sorry about that. Good. Final result is then well, we had the AN distribution, so we converted it to the delta R distribution. Looks like this. Yeah, we put this Prax result there as well, so we're definitely consistent, but on the low side. Our uncertainty is competitive, so really a bit smaller than Prax, like 25% smaller. I have to say that if you look in the literature, then there's other measurements. Well, we heard about it this morning. Okay, so there are more accurate measurements. These, well, I don't know if I would call my own measurement model independent, but it's a very new alternative way to see it, and that's the result. Yeah, that's it, right? I mean, the oxygen neon, you have to come back next week.
All right.
Thank you. Yes.
Cross sections are hard to measure. So how do you know that you're measuring the cross section?
Theoretically or experimentally? Well, I don't think so. So this is the lead cross section of. So there are two parts to it. The one is the number of events. The other is the luminosity. But the luminosity is this Van der Meer scan. So this dominates actually the uncertainty. It's a 2.5 to 2.2% uncertainty. And the luminosity is, yeah, if you really kind of try to estimate how much lead is in your beam, and well, they know how to do this. Then it's a question of estimating how many events you have. And that's a little bit subtle. No, that is subtle. But actually, this at least detector is really accurate. So this is the distribution of all the events with their V0 amplitude. So, okay, so it is true that it is very subtle because most of the events have a very low amplitude. So for the high multiplicity, it's obvious if you have an event or not. There are 10,000 particles. But if there is like 20 particles, do you have an event or not? So this part is the most difficult one to estimate, but at least as efficiency measurements, and up to like 90%, which has like an amplitude of 80, they can do this with 100% efficiency. Here they cannot, but since we understand the distribution quite well, I think there's, well, this 10% has an uncertainty of 1%. So it's a 10% uncertainty on the 10%.
Can I react to that? That's a log plot.
Well, here's a zoom in.
You
So
say
here's zoom in.
you have a lot of problem. You have a lot of problem with knowing exactly where you are in terms of centrality and efficiency towards the left side, because that's zero multiplicity.
Yeah.
But then the cross section is going up exponentially there.
Well, this
Did
is
you
zoom.
tell me at the end you can
This
get
is the zoom of this. So you really have to look at this piece, and then it's not so. It's still log plot, but it's not as so logarithmic anymore. Yeah, I'm just saying that this is a good detector, and they know what they're doing.
But then where is 1% on that curve?
No, it is so to 90% they know, and then this part is
That's 10%.
estimated, and they estimated 10% uncertainty how many are there here. But they also measure still a lot here, and they also have a lot of background and noise here, and they estimate all that. So I don't know. I would
just 10% of the cross section between that line and the top and the exactive.
Yeah.
And you think you could measure that to 25%? 2.5% or 1%? What is?
Yeah. Yeah. I mean, I'm not an experimentalist, but I wouldn't trust this.
Shusha.
Yeah, just a quick comment on your system dependence on the V2 over epsilon
Yes.
coefficient. So my understanding is the reason why we observe, well, we means I myself also observed this in some work. So we observed this because the mean PT of these two systems they are not identical.
Yes.
And here the absolute, the V2 is measured only for some particular range of PT. So that means the mean PT of these two systems are different, so that the cutoff region of, I mean, the V2 of the cutoff region captures V2 different of the whole region. That's why we could observe the system dependence on top. However, if you do the same analysis, not for identical centroid range, but for identical multiplicity range, I would expect the difference to be smaller because mean PT is expected to be smaller there. Mean PT, sorry.
Generically, I mean, this is so close that you can do this. Generically, I don't like to do the same multiplicity versus same centrality, because centrality is very nice because it really says something about the overlap and the geometry. The multiplicity. But okay, I mean, we can for this system you could try this and this is doable.
But you already mentioned that this is not identical centrality. They are simply I mean that there are some difference in the margin of this.
That was not my choice.
How much closer to if you do a different similar multiplicity guys? How much does the discrepancy go?
Well,
down
I mean-
to a similar multiplicity.
But the proof is up to you. I mean, I just saw here that if you do it like this, they're different. If you say, okay, you do it first multiplicity and I do different PT cuts that I agree. Well, if you show it, then I believe it.
Hold on a second, we've got a question online. Zidu, can you unmute yourself?
Yes.
Yeah, okay, thank you so much. So I found this talk very interesting, but sorry, I don't know too much about the heavy ion fusions. I just want to make sure that I understand. So when two nuclei are somehow colliding with each other, will they be somehow deformed? I mean, so
Which was deformed?
yeah, the deformation of the nuclear structure. Will we see a great deformation of those nuclear structure?
For which ion? For lead?
I'm sorry.
For which ion? Which nucleus?
Maybe, yeah, for example, maybe the gold or maybe lead that you previously talked about.
I think lead in this case is doubly magic, so we assume here it's just spherical.
Yeah, right. So, but for the gold or the zirconium, I mean, when you are somehow colliding them together, will they be somehow deformed?
Yeah, so yeah, I was very fast, but there are these kind of 5 cases and there are different colors and there's different parameters. But okay, since we have these nice 3D pictures here, it's relatively clear how they are deformed. There's a pair, there's an ellipsoid, but okay. That was a bit fun. With zirconium and ruthenium are deformed. That was the topic of this talk.
Okay, so yeah, I'm just wondering. So because you talked about the neutron skin of the lab QA, so can you somehow why you can measure the neutron or the proton distribution of the lab QA by using
yeah, I mean, I'm not sure if I would call it a deformation. In our terms, not because it's still spherical. But yeah, we vary the neutron skin, so it's deformed in that sense. But it's just wider or smaller. It's still spherical.
Okay, so the lab QA is still spherical. That's good. Yeah, because somehow I'm just wondering. I mean, the parameters that you extracted from the heavy ion collisions are still from spherical nuclei, not from deformed nuclei. If that is deformed, then you cannot simply compare it with the P-Rex experiment. So that's what I want to say.
Thanks.
Okay, great. Okay, thank you.
So I think we're pretty much out of time. Let's take a coffee break and then leave any other remaining questions for discussion.